So you've tuned all your indexes. You've created perfect schema. You've spent hours and hours and hours and hours and hours writing really complex, convoluted T-SQL. Any of you do that? Your query is still slow. You have no idea what to do next except move to Oracle. That's what we're going to talk about today. What do you do next? Where do you go? We are going to focus on your large, really long-running queries. People who do data warehousing, well, especially analytical data warehousing. This talk is really just for you. Those of you who do OLTP, maybe not quite as appropriate, but maybe you'll learn something interesting. We're going to talk about doing analysis on sets of data. The more complex the logic, the better, especially logic that crosses row boundaries. Look-back logic, rolling aggregates, things like that. Things that maybe window functions can help with, or maybe not. We'll see. And we're going to try to focus on solutions that are reasonably simple. And I don't think I put reasonably again before reliable. They'll be reliable. And they'll be reasonably simple, but not super simple. But that's OK. You'll see it's actually simpler than the alternative. So a little bit about me. I come from Boston, Massachusetts, in the United States, obviously, in case you can't tell by my accent. I work in the financial services industry primarily as a data warehouse specialist. I've written some books, SQL Server 2008 internals, Expert SQL Server 2005 development, and about 5 or 6 others over the years. Some more coming up next year, so keep your eyes open for that. I speak at a lot of these things, and I have a website called SQLblog.com, which I hope you will check out after the show. There will be all the stuff from this session and my other session posted there, probably late in the week, because I'm going to deliver this same session and the next session in Amsterdam as well. Finally, I always love a good chat, so drop me a line, amachanic@gmail.com, if you're lonely or whatever, and we can become pen pals. Anyway, what we're going to do is break this into 2 sections. Section 1, we're going to talk about data manipulation options. We're going to dive right in, by the way. This is 0 to 500 right after this slide. So we're going to start right away with options for data manipulation, and then we're going to get into a case study, and that's it. So get ready. I hope you've had some coffee. Let's go. So how do we manipulate our data? Well, if we're like most people, our application calls into a query. Maybe it's in a stored procedure. Maybe it's in a view. Maybe it's in a UDF. Maybe it's a bunch of things all joined together. Whatever. Our application calls into the query. The query, at some level, reads the data from the database. The screen gets messed up, and so, well, you don't need a presentation because you have a database, and you're reading data from it, in theory. So this is what happens when you use SQLCLR too much. This is what happens when you start to talk by mentioning Oracle. Oh, I've angered the demo gods already, so. It should. Here, let me see if I can do something on this end. Oh, wait, you know what? It went into the wrong mode. Not good. Well, hold on. I'm turning it back into the correct mode here. Yes. OK. I think it is, yeah. No, I didn't change it. OK. So where were we? Oh, so your application calls your query. Your query reads from the database, and the data streams back, and your user maybe is happy. This, just like any other method of doing anything in the world, has pros and cons. So let's talk about some of those. So pros, this is the way we do things in the database, right? This is the basic SQL Server way of doing business. It's, in theory, simple. Later, we'll challenge that notion a little bit. But in theory, it's simple. Most developers know how to write select star from table where blah, 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 and get a nice index scan. There's no cost associated with data movement within SQL Server. Maybe, I mean, there's obviously a cost with moving the data from SQL Server over to your application, but there's no internal cost. Since we're talking about SQLCLR, we do have to bring that up, because we'll see that later. Cons? Well, what we're going to see is that some queries can be very, very complex. Of course, you all know that, having written some T-SQL in your time. Performance, very difficult to control. Very, very difficult. We spend a lot of time doing performance tuning. We're at the mercy of this thing called the query optimizer, and if it has a bad day, we have a bad day. Not a good situation to be in. So what's an alternative to this? Well, we could use SQLCLR, and if you've read anything on SQLCLR, the basic method that's always shown is that your application calls, again, into maybe a UDF, maybe it's a stored procedure. Internally, that stored procedure makes use of this thing called the context connection, which can reach back into the calling context of whoever the caller is. So if I log in as Adam Machanic, I call my UDF uses a context connection. That context connection is Adam Machanic at that point in time. It has access to all the things I have access to. It calls out into another T-SQL statement effectively internally. The context connection uses ADO.NET, just like anything else, in .NET to access data. So it calls a second T-SQL statement inside, or maybe a stored procedure or whatever. That calls back to the database. The data flows through ADO.NET, through the context connection, back to our original connection, back to the caller. Okay, why would we want to do this? Well, maybe, in some cases, this is actually faster than T-SQL. Why is that? Because we can take advantage of the fact that .NET is compiled, and we can control performance ourselves to some degree. The integration model is really nice here. By seamless, what I mean is that if we have an existing stored procedure in the database, or an existing UDF in the database, and we want to replace it with a CLR version, or the other way around, we can do that all day long, and our users or our applications don't have to know the difference. The integration is completely seamless, such that you can swap these things back and forth. Very, very simple to develop if you know basic C#, and by basic I mean C# that you could learn in 4 hours. You can write a CLR stored procedure, no problem. This is not like WCF programming or something like that. This is really, really easy, basic stuff. Of course, there's some cons. We're introducing the data transfer overhead that I mentioned before. So now, of course, we have effectively 2 SQL statements running, and we have this middle layer. Now, that overhead isn't huge, but it's there, and we do need to mention it, because this is a performance talk. We're introducing a management overhead. And now we have, in addition to our database, and in addition to all of our database code, we have to worry about assemblies. We don't like to worry about extra stuff, but it's maybe the cost that we have to pay. And finally, the biggest problem by far is that this is an inherently single-threaded model. So I started working with SQLCLR stuff quite heavily, and I found I was able to get really, really good results. But then I started feeling limited by this single-threaded model. And I started thinking, how am I going to get past this? I have 16 cores in my server, 32 cores in my server, and I want to solve a really compute-heavy problem. How am I going to use those 16 or 32 cores and not just use 1 core? How am I going to scale? So I thought, what if my application called into something, stored procedure, UDF, and what if that thing knew how to talk to a threading library? Well, then I could do something very interesting. I could have my threading library make multiple simultaneous calls into ADO.NET, call multiple simultaneous queries, which will simultaneously read from the database, bring all the data back through my threading library, merge it together, back into my select, out to my application, and now I'm taking advantage of all my cores. Now I can no longer use the context connection. I have to use a loopback connection instead, because when we're working with the context connection, we only have 1 of them per session at any given time. The loopback connection is a typical ADO.NET connection. It presents a slight security issue in that now my loopback connection has to have access to everything that anyone might want on my server, on my local server or my local databases. So maybe we introduce a slight security issue. We actually have pretty good performance here because we have lots of threads, and the loopback connection can participate in ADO.NET connection pooling. So very, very fast to get those things. Our pros, I found when I wrote this, and you're going to have a copy of this in the downloads. This threading library delivered excellent performance. Fantastic. Very, very scalable. I can scale almost linearly up to as many cores as I want, bring all the data back. It's a beautiful thing. Unfortunately, it made me feel a little bit dirty. The model is very complex, and it's brute force in the best of cases. Basically, I'm doing in SQL Server all the things that you're not supposed to do in SQL Server. And I'm doing in SQLCLR, I mean, it's even worse, because I'm doing in SQLCLR, this is like the most unsafe library you can write, basically. All the unsafe features in SQLCLR are packed into one library that does all this work. Works really nicely, but it makes you feel a little bit on edge when you use it. So after about 1.5 years of using this library, I sat back and I thought, what are my real goals? What am I really trying to do? So here's what I'm trying to do. At the end of the day, I want to read data, obviously. I want to analyze the data. I want to return to the caller a table-valued result. And most of all, I want to be able to scale. I want to be able to parallelize. And I started thinking a little bit, brainstorming. And I thought, interesting, we already have a construct in SQLCLR that does almost all this stuff. And this construct is the user-defined aggregate. User-defined aggregate, by definition, reads data in, and it reads it in one group at a time. That might be important. We'll see why later. It analyzes data. That's what aggregation is. It's a form of analysis. And with a user-defined aggregate, that analysis can be whatever you want, right? I can put any algorithm I want in my user-defined aggregate. It's just C# code. User-defined aggregates support parallelism, so they give me the scale I want. Unfortunately, there was a little bit of a problem. User-defined aggregates, do they return a tabular result? No. Scalar result. So how am I going to deal with this problem? So I'm so close, so very close to my goal. Well, what I realized after a bit more brainstorming, this is like 2 years of brainstorming we're talking about here, FYI, just packed into this talk, is that I could take a user-defined aggregate, and let's read this one from the left to the right instead of the other way around. So the data comes out of the database, goes into a user-defined aggregate. The user-defined aggregate returns a pointer of some sort to a table-valued function. The table-valued function takes that pointer, decomposes whatever's behind it into a tabular result. That goes back into my select, and that goes back to my caller. And now I've achieved my goal. I have really nice integration with the query processor. The query processor knows how to deal with aggregates and how to deal with table-valued functions in a really good way. Everything is completely parallelizable, and not only is it parallelizable, but it's natively parallelizable. I don't have to use a threading library anymore. It's completely safe assembly, and I no longer feel especially dirty. So it's very, very nice. Cons, once again, always. We now have 2 CLR components in the mix, so we have even slightly higher data transfer overhead. Our T-SQL is going to become more complex than it would with a standard CLR solution, but still maybe less complex than with T-SQL. And we're opening the door to a little bit of temperamental behavior because we're doing things that the query optimizer maybe doesn't know that we're trying to do or doesn't think that we should do in various cases. But that's okay with me. Again, you have to accept sometimes the bad with the good. So how are we going to get the data from the UDA to the TVF is the next question. And there's 2 options for that. Option number 1 is the slow option for people who want to play it safe. You could return anything you want, any scalar value from that UDA, right? So you could return a binary, var binary max, or you could return an XML document from that UDA, and you could take that, and you could pull it out of the UDA, and you could pass it back into some TVF, into a big, huge lob argument, and you could decompose the thing in there, and you kind of get the behavior when you want, and it'll be really, really slow because we're passing things around. I don't like that. So what I do instead is take the fast and very, very, very slightly dangerous method, which I'll show you today, which is that I keep some data around in memory, and I trust that it will be there when I come back for it later. And that's what my pointer points to. In theory, there might be an edge case where the garbage collector would kick in at just exactly the wrong time and destroy this, but that's very theoretical and has not happened to me in any of my testing, so not a concern. And what I do is, yes, Hugo?
In the theoretical edge case, what would be the result?
You're always into the theory, Hugo. In the theoretical edge case, what would be the result? An exception, in my case, because I'll put in a check to make sure the memory's still there. So it shouldn't be a big deal. So what do we do to use the memory the right way? Well, we have to set up a centralized collection. It has to be static, so all of our threads can see it and share it. And it has to be protected in some way. And I've actually written a fairly nice lock-free data structure that we'll look at later that can actually do this work for us. From the UDA, we return a GUID or an integer key that can look into this static collection. Or, if we really, really want to be creative, our GUID or int will be completely meaningless, and we can do all of our work internally inside CLR. We'll get into that in a little bit. The UDA result goes into the TVF, and the TVF streams back the data. In any case, we have to be very, very careful of this thing called partial aggregation. This is one of those temperamental issues that I mentioned before. So SQL Server has this feature in parallel plans where it can do, so it'll read the data out of the table, and it'll do some aggregation on whatever, so when the data is read out of the table, some rows will be read on some thread, and some rows will be read on another thread, and some rows will be read on still some other threads, hopefully. And let's say you have products 1, 2, 3, and 4. You can have thread 1 with rows for products 1 and 2, thread 2 with rows for products 1, 2, and 3, thread 3 for products 1, 2, and 4, and so on and so forth. They're all kind of mixed up. And so what SQL Server will do is it can aggregate a little bit on each thread, the rows as they are in that form. Then it can take the smaller result, since aggregation reduces the number of rows. It can move those smaller results across threads and re-aggregate again to get the final answer. It's called partial aggregation. The problem with partial aggregation when we're doing heavy, big, table-valued analysis is memory utilization. We'll have all of the data that we read out of the table in memory all at once, in theory, and we really want to avoid that situation. So if you see a query plan with partial aggregation, you're doing it wrong. But I'll show you the query shape in just a bit. Let's talk about a case study that we're going to apply to all these methods and actually see how this is going to work. It's called the overlapping intervals problem. And the overlapping intervals problem is a really interesting T-SQL problem that involves quite a bit of work and jumping through hoops to solve efficiently in T-SQL. And even once we've solved it efficiently in T-SQL, we're still not all the way there. So here's what the problem involves, basically. Let's say that we have a bunch of intervals. So in other words, they're time periods. They have a start date and an end date. So interval 1, let's say, starts June 1st and ends July 15th. Interval 2 starts June 15th and ends July 25th, and so on and so forth. And at each point in time, we want to identify exactly how many intervals were active at that point in time. This seems like kind of a weird problem if you've never worked with time series databases, but as soon as you get into something involving heavy time manipulation, overlapping intervals problems and other date problems such as gaps and islands become really, really, really common. So here's how effectively, logically we solve it. We break everything up along interval boundaries. Every time we have a start or an end of an interval, we put a line, and then we just walk logically, and we count. So in the first line, we have 1 active interval. In the second line, we have 3 active intervals, and then we have 2 active intervals, and 1, and 1, and then we have 2, and then we have a gap, and then we have 1 active interval. Now if we look at this data and we bring it into a different form, what you might notice is that the gap between those 2 1s in the middle is fairly small. Often with overlapping intervals problems, we want to ignore very tiny gaps. So we add a further constraint, which is that, let's say, any gap of less than 1 day, we would want to ignore and just pretend like it didn't exist. And so we wind up with something like that as our final result. Now, start thinking about how you'd solve this in T-SQL. You'll need for each row some kind of look-back logic. You have to look back and make sure that the prior interval ended within the gap tolerance range, and you'll have to figure out how many prior intervals there were that landed and overlapped with where you are today, and it gets a little hairy. So let's go out and see how we can solve this. So what I'm going to do is go into Management Studio, and to set this up, I've created a database called Hotel Sample. And the Hotel Sample uses data that I created that emulates the largest hotel chain in the world. I can't remember which chain it was at this point. I wrote this back in June of this year. Damn, okay, well, that's all right. Anyway, the largest hotel chain in the world, and they had a certain number of hotels. Let's see how many there are. It might have been Hilton, but I don't think so. So there's 4,000 hotels in this chain, and there's a certain number of rooms at each of the hotels, right? So this Heather Hughes, these are all actually sourced from the AdventureWorks database, all these names. So I took the names and I kind of randomized it a bit, and I optimized for a certain number of rooms based on the research I did for the biggest hotel chain in the world. So this hotel, for instance, is a little boutique hotel, and it has 17 rooms. This one here is a bigger hotel, and it has 173 rooms. Each night of the period that we're working with, we insert into a table called hotel stays, and each night a certain number of rooms are occupied at each of the hotels. So each time someone stays, they get a unique stay ID. They stay at the hotel, they have a check-in date and a checkout date. And so each night, a certain number of people are checked in and a certain number of people aren't checked in. And our goal is simple: find out how many people are in the hotel each night, or are in all the hotels each night over a time period that we're going to analyze. So I started working on this in T-SQL, and my T-SQL skills are pretty decent, but they're not the best in the world. And I wound up with much slower solutions than I wanted, so I decided to find the best in the world. And I called my friend Itzik Ben-Gan. Hopefully you've heard his name. He writes a lot of T-SQL books, and he happens to be arguably one of the best in the world at T-SQL. So I said, Itzik, can you please write me a query to solve this problem? And he actually happens to be really, really into time series based problems. So he came up with this solution. He actually sent me, he got really into it, and he started sending me like 8 different queries over the course of a 3-day period. And each one was faster and faster and faster than the prior one. And he finally sent me this query, and this is his fastest version. This query is brilliant, I should add. So this query involves, okay, first of all, look at this query. No mortal can grasp this query on their first pass through it. This query involves basically you take all of the, what is he even doing here? Oh, you take all the starts, the check-in dates, and you put a +1 on those. And you take all the check-out dates, these are the end ordinals, and you put a -1 on those. And then you order them all together, and then you walk forward over the results. You put a row number over there, and you use the lead function, and you do some addition. And so you walk over and you do, every time someone starts a stay, it's a +1, and every time someone checks out, it's a -1, and every time you get to a 0, that's kind of the end of an interval. And so he walks along, and he uses lead, he uses lag, he uses row numbers. It's a crazy, crazy query. It's brilliant, but this is what I'm talking about. This is the kind of thing we have to do in T-SQL to solve these sorts of problems. So I'm going to run this query. And we're just going to run it for 500 of the hotels. We won't run it for all 4,000 of the hotels right now. Actually, I'm going to run it. So it takes about 7 seconds to run for 500 of the hotels, which seems pretty reasonable. And the query plan looks something like this. It's a single-threaded plan, and we get a seek on the hotels table. And then for each hotel, it goes into a loop. and it has all this stuff back here that has to be done. That's all the logic, and it comes through all that logic, and the results come out. Well, so anyway, I wondered, of course, could I solve this with SQLCLR? Well, probably, right? We're in the session on it. So the first thing I want to do when I'm trying to come up with a CLR solution is find out how long it takes me to actually read the data into SQLCLR. Not do anything with it yet, because doing stuff with it takes time. I have to write the logic. So the first thing I do is I write a quick wrapper that just reads the data in. And I figure if I can read the data fast enough that I have a little bit of headroom, maybe I can write a clever C# algorithm and actually end up net positive. So the first thing I wrote was this thing called read hotel stays. And all it does, you pass in a min hotel ID and a max hotel ID. It pulls up a context connection. It opens up my context connection, and it reads from the hotel stays table, where the hotel ID is between the min hotel ID and the max hotel ID. And then at the end, it tells me how many rows it read. Okay? That's all it does. I've already deployed that to my database. And now its solution ran, let's get the actual CPU time here. So its solution ran in 5.3 seconds. So we want our CLR solution to be able to beat 5.3 seconds. Let's see how long it takes us just to read the data into the CLR space. Read hotel stays. So it took about 3 seconds that time, but there was a little bit of JIT overhead. That's just-in-time compilation. So that will only happen the very first time the very first user runs this. So let's run it again and see if we can get slightly, there we go. That's what I wanted. Now we're at 1.9 milliseconds. And from here on out, until our app domain gets cleared, everyone will get 1.9 seconds for this run. So that's really just the very first user that hits that overhead. So we have 3 seconds to play with. 3 seconds in C#, that's a lot of time. I think we can do this. Otherwise, I wouldn't have a talk for you. So what I wrote was I implemented an algorithm, and I put it into a class called interval counter. And interval counter does the same thing as its query, but it does it in a more generic way, because it'll count, it doesn't know about hotel stays or anything like that. All it knows about is intervals. So if I had hotels in one database and prescription drugs, maybe start and end periods for prescriptions in another database, that's another scenario for this kind of work. I could use it for both of them seamlessly, no problem. That's another benefit of SQLCLR. So anyway, I've written this, and it kind of uses a pattern similar to CLR user-defined aggregates. It has an init method, has an accumulate method, and it has a terminate method. The terminate method returns an IEnumerable of something called result. And result is just the result of a count operation. IEnumerable is basically the .NET streaming interface. So it streams back the results one at a time. Now the input to this work, accumulate, is a start date and end date, but they are implied to be in order. They have to be sent in order. And that way we can stream the results into the class and then back out of the class without holding on to much in memory at any given time. And that's important, because when we're working in SQL Server, memory is at an extreme premium. SQL Server, if you think about it, is a very expensive product, right? I don't know how much it costs now, but it costs a lot more than it used to cost. And it certainly costs a lot more than your application server costs. So if we're going to do the work on the SQL Server tier, we want to make sure that we use every cent to our advantage, and we want to make sure that we limit our use of memory and compute time where appropriate, so that we can take advantage of the money that we've spent, the investment we have. So our accumulate method takes our start and end date, and basically the algorithm here's the algorithm, that's it, that does the actual work. It's pretty straightforward. All it does is it walks along. Every time you get a new start date, it checks all the dates it's already gotten, counts how many overlaps it had, and then outputs the result. That's it. Dead simple. It took me about 10 minutes to write this in C#. It's brilliant guy. Took him 2 days. I don't know how much time he actually spent on that, but it was like 2 days of work. And it would have taken me a year to write that same query that he wrote. So point is, C#, a little bit easier for a lot of us developer types. Now, once I have my interval counter, I can take it, and I can put it into a store procedure, user-defined function, or whatever. And here I've written a store procedure called get hotel stay interval counts. It takes a min hotel ID and a max hotel ID. I read in the data, just as I did before, on the context connection still. And then I instantiate my interval counter, and I start passing the data in to my interval counter. Where am I passing the data in? Somewhere. Well, let's just go to, it doesn't matter. Anyway, accum. There we go. So I accumulate the data into my interval counter. Then I ask for the results back. I use for each, which I can use on my IEnumerable, and I stream the results back 1 row at a time, and everything's good, we hope. Let's go try it. So we had, what were we at before? 1.9 seconds. We're trying to beat 5.3 seconds. Get hotel stay interval counts. And my C# was pretty decent, as it turns out. 2.9 seconds, so I'm net positive as compared to ITSIC when we're processing 500 hotels. Not bad. Now let's see how it scales. I'm going to go back here, and I'm going to run ITSIC for 4,000 hotels. And the results start coming back. Now, naturally, it's a little bit slower because it's running for a lot more data. Should have been finished by now. So ITSIC took 48 milliseconds of CPU time, but only 17 seconds to run. Actually, let's run it one more time, just to make sure we get like any caching out of the way. I don't want any questions like, oh, the data wasn't cached that first time, so you did a disservice to ITSIC's query. There we go. So 9 seconds now, which is what I was expecting. So 71 milliseconds of CPU time. Only 9 seconds elapsed. The reason is the query optimizer did the right thing in this case, and it saw that we had a lot more data, and it gave us a nice parallel plan. Beautiful. Now let's go back to my read hotel stays. So now what are we targeting? Let's be exact here, 9.4 seconds. I'm going to try to read 4,000 hotels into my hotel stays. And things are a little slower, aren't they? My read hotel stays uses the context connection, and I can't even read the data in 9 seconds. So now ITSIC wins. I can't let ITSIC win. 14 seconds just to read the data. It hasn't even gone into my C# logic. I'm not even going to run that. That would be a waste of time. So this is where I came along, and I created this thing called the query parallelizer. And the query parallelizer is a class, generic class, query parallelizer of type T. T is the return result. And what you do is you pass in your query, and you pass in a couple of variables. So you write your query as select from table or whatever, where some integer is between @x and @y, where @x and @y are a range of integers over which you want to process. So you tell query parallelizer my minimum variable, that's my minimum range, is @x, my max is @y, and you tell it my min value I want to process, let's say is 1, and my max value is 4,000, and you tell it I want you to work on this many threads. And what the query parallelizer does is it goes out and it fires up, let's say you ask for 10 threads. It fires up 10 threads, and it gives the first thread 1 through 40 in the example I just gave, and it gives the second thread 41 through 80, and it gives the next thread 81 through 120, and so on and so forth. And so all the threads are working in concert at the same time. They bring back the data flows through a lock-free data structure, gets pushed back to the caller, and things tend to work pretty well. Here's how you do this work. Actually, let me just show you the code really quickly. Go back here. So this is called get hotel stay interval counts parallelizer. So what I do here is instantiate the query parallelizer. I give it the same query as before, but I give it a min hotel ID and a max hotel ID variables. I give it the min and max values. I tell it how many threads to process on, and then I give it a delegate, which is a C# pointer, effectively, to the function to process the results, which is, of course, my interval counter. All right? When I go to my T-SQL, this is how I count the thing, or this is how I call the thing. I declare min and max hotel IDs. I want to give it a number of threads to work on, and I want to be fair. So I'm giving it the same number of threads as my max stop in my machine. So I'm going to let it do the right thing, and then I'm going to go ahead and call it. And the results come back pretty quickly. We're now down once again to our single threaded time of 3 seconds. And we're actually beating the ITSIC algorithm now by a factor of 3. Not bad, except, of course, for all the caveats I told you before, and the fact that I feel dirty. So let's try our final methodology. Let's move a little bit further in. And let's start with reading into an aggregate. Again, just like the store procedure, I want to read the data first and see how well I can do. And this is always an interesting thing to do, because as you read data into SQLCLR using different methods, store procedure versus aggregate, or in other words, ADO.NET versus passing the data directly into your method via the mechanisms that SQL Server uses for that, what you'll find is that they have different scalability characteristics. When you're reading the data in and you aren't reading a whole lot, it turns out that the store procedure versus the aggregate method scale relatively well together. As you read more and more data into the aggregate, whatever mechanism the SQL Server team used to do that work gets a little bit slower over time. It's not about more rows of data, it's actually about bigger row size. Whatever they did doesn't work very well as you get really, really big. If you have like lobs and things like that. And this is why it's important to kind of try both of these methodologies each time. Now in this case, we're not passing a whole lot of data. We're just passing a couple dates in. So the aggregate tends to do pretty well. And here's how we're going to test it. I'm going to create an aggregate here. It is a natively serialized aggregate. Accumulate takes a start date and end date, and all it does is increments a row counter, because I don't want to do anything. I just want to pass the data in and count the fact that I saw a row. So when I go back here, now my store procedure took, what, 2 seconds to read in the 500 rows? Let's see how long my aggregate takes. And here's how it works. I read from the hotel stays table. I group by hotel ID. I aggregate. And that's it. So for our 500 rows, instead of 2 seconds, it actually took, is that right? It was fast. It took 313 milliseconds to read the data. So the aggregate in this case scales really, really nicely. What? Sorry? No, when the first read I did was this one. Right? So that's equivalent. So this is the first read. We'll run it again. This is into the store procedure where we're only reading 500 hotels worth of data, and that takes about 1.8 seconds. Again, that uses ADO.NET. So ADO.NET has some overhead, and when it first does that call, there's a little bit of startup overhead there. The aggregate doesn't have the startup overhead, but later, if we were to increase this and start passing lob columns or something like that, you'd see the flip side of that coin. So 2 seconds or so for the store procedure, only 300 milliseconds, and we can run it once more just to verify, because that did seem a tiny, oh yeah, that's fast. That thing ran almost, oh, there it goes. That time it took 720 milliseconds. These timings are very accurate, as you can tell. But anyway, my execution plan is really nice. Now, when I said that the CLR UDA and TVF combination have a really good query processor integration, that's it. I mean, this is a beautiful query plan. We read some data. We calculated some kind of scalar, getting the data ready for the aggregate, and then aggregate it and return a scalar. That's like the easiest plan in the world. And that's the wonderful thing about SQLCLR, really, is that it's really nicely integrated with the query processor. and still lets you program things and still lets you control things the way you want. And once you have the data read, and once you know that you can read it fast enough, which I think we've just verified, what we can do is write our table valued aggregate, and here's how it works. First of all, we need an aggregate, so I'm going to call it interval ag. And internally, the aggregate uses this thing called boundless array. And this is that lock-free data structure I mentioned before. And this is a data structure that I wrote that basically, it's generic. And so it's going to have instances of my interval counter. And it looks like an array in that it takes a number as an indexer. But it's boundless in that you can pass any number between 0 and max int 2 billion whatever as your number. And it stores it in a sparse format so it doesn't use much data. And it's also optimized so that it doesn't use any lob space at all. And by lob space, I'm referring to the CLR large object heap. It doesn't use any space at all in the large object heap. So it's very, very memory efficient, and it's fairly fast within SQL Server. A good way to store data. Now, the reason I want to use the boundless array is that I want to be able to look up my values based on something that I don't have to pass back and forth between the UDA and the TVF. And as it turns out, we have that something available to us all the time, and it's a managed thread ID. What we're going to do in our query plan is make sure that each instantiation of the user-defined aggregate and the table-valued function run on the same thread within SQL Server. Therefore, they will have the same managed thread ID every time they call into the CLR space, and so we can use that as our indexer to get the data. As a result of this, we actually don't need anything serialized out of the UDA. We don't need to return anything. So I'm creating this byte called, you have to have something in the UDA, or the SQL Server complains and says, why are you creating a UDA that doesn't return anything? Well, I don't want to return anything, so I'm going to use the smallest data type I can, which is byte. It doesn't accept Boolean, unfortunately. And I'm not going to put anything in this byte. It's just a meaningless byte so that SQL Server thinks that I'm returning something from the UDA. That's important. It does need to think I'm returning something so that I can force it to call the UDA first and then the TVF second, but it doesn't have to know whether or not that thing is meaningful, and it has no way of knowing whether that thing is meaningful. So here's how it works. I instantiate my boundless array. When I accumulate, I call counter.accumulate. Counter is just a wrapper right here that goes out into my boundless array, grabs the interval counter for the current managed thread ID, accumulates the data into it, and when I terminate, I simply return 0. I can return 0, again, because I'm going to use the same managed thread ID when I call back into this thing to get the data back. So let's go here to my table valued function. My table valued function takes an integer called interval ag value. Of course, it's just the meaningless 0. It doesn't really care. It asks for the result in interval ag.counter. Again, that's that wrapper that goes out and resolves using the managed thread ID. So it calls counter.terminate. It iterates over the results, and it returns them one at a time. Each of the results comes back to SQL Server. SQL Server calls the fill row method, which is interval values underscore fill. We convert the results. They come in as an object, so we cast the object as a result, set the start dates, end dates, and counts, and that's it. That's all we have to do in this case. And it's because I wrote the logic in that other class, the interval counter. Over on the T-SQL side, it's a little bit more complex. Here's what we do. For each hotel, logically, well, actually physically, for each hotel, we call into the hotel stays table, and we grab the hotel stays for the hotel that we're working on that pass. And we calculate a row number over the check-in date. Now, the reason we need this row number is to enforce the ordering. Remember that the interval counter needs the start dates and end dates to be, or the start dates at least, to come in the correct order so that it can do its streaming work. So we're going to force SQL Server here to either use an index on check-in date if it has one, or to order the results itself. I like to use SQL Server to do my sorting because sorting is a fairly expensive thing and SQL Server is fairly good at it. So I let it do that work. Now I take my data from here, we call that HS, and I call into my interval aggregate, and I pass in my check-in date, my checkout date, and I have a 1 hard-coded here, but instead I need to pass in hs.r, which is my row number. That way SQL Server is forced to calculate this row number. Now interestingly, inside of my aggregate, I take the row number in the accumulate method, but notice I'm not doing anything with it. This is yet another example of where SQL Server is forced to calculate the row number so it can be passed in, but it has no clue what's going on inside the CLR aggregate. So what we're doing is just playing a little game with the query optimizer. We're making it do some work on our behalf so that we can get the data in the right order, and we force it to do the things by passing the data around our methods, even though it has no idea what we're actually doing with them. So it's an interesting way to play some little games. So we calculate our row number again. We go into our interval aggregate, pass in our check-in date, checkout date, and R, which is the row number. Then this will output a 0. This 0 gets passed into the interval values table valued function. Yes, Thomas?
Do the nested select, or could you just do the interval ag directly next to the row number?
The question is, do I actually need the nested select, or could I do the interval ag right next to the row number? The answer is yes, I could do the interval ag right next to it. I could actually do all of this in a single derived table instead of 2 derived tables. I just think it's clearer to read in this format. So, but then like the row number would have to be right here, which I think is a little confusing. It would look like this. I think it would look something like that.
I'm wondering whether you don't even need to pass the row number.
That's ugly. This whole thing's a little ugly, and that's really ugly.
Do you actually need
So,
to pass the row number into the function, or could you just put it out?
do I need to actually pass the row number? Yeah, so the optimizer is smart enough that if I do that,
But if you move the row number outside,
no, because it needs to be done first. I need to guarantee the order. And the optimizer is smart enough that if I do this, it won't calculate the row number at all. And if I do it somewhere else, it's not guaranteed that it's going to pass it in first. Actually, in this case, I don't need the row number at all because I've guaranteed that the index order is correct. But I would still put the row number because that guarantees that none of my other colleagues who maybe wouldn't understand quite as well what I was doing here would come along and mess it up. So guarantees are a good thing. When you're playing games like this, you want to guarantee as much as you can, right? So that you don't screw things up for someone else down the line. Anyway, our aggregate produces, I call it an aggregation token, but it's just 0. But it's important 0. It's a very important 0 because SQL Server doesn't know that it's a 0. It thinks that it's an integer that we want to use for something else. So when I calculate it here, I pass it here, and the optimizer has no choice but to first call the UDA and then call the TVF using that value in that order. And that's important, of course, because if it's not done in that order, we'll have no data and the whole thing breaks. Well, that's not good. Anyway, our interval values is called V, and once we've called that, we simply pull out the start date, the end date, and the number of rooms. I had to convert the start date and end date to dates because Visual Studio, which I used for my deployments, doesn't work with the date data type, and I was too lazy to go in and change it. So it's date time in the output here. But you can actually change that if you want. Anyway, let's check out the query plan. Oops, that's for later. Maybe. So here's the query plan. We get a nice parallel query plan. We go out to the hotels table first. We loop on each hotel, one at a time. Go back to hotel stays. Segment and sequence project, that calculates our row number. Compute scalar gets the data ready for the aggregate. The data goes right into the aggregate. Then for each row that comes out of the aggregate, guess how many rows come out of the aggregate per hotel? 1. It's not grouped by anything, but it still has a nested loop here. For each row that comes out of the aggregate, it goes into this loop, calls into our table valued function, comes back with our compute scaler to calculate the date, brings the data back to our select, we run it, and 2.9 milliseconds. I'm pretty happy with that. At the end of the day, I have less code, faster query. I have something that is not using threads and synchronization and other things in ways that you're not supposed to do in SQL Server. And I've solved my problem. And I can go home and watch TV or do something better with my time than play with T-SQL. So I'm happy. That's what SQLCLR is all about. It's a happy maker. So we have a few more minutes. Are there any questions at this point? Erlen.
So you said that you put in the row number there because then the optimizer has to call the aggregate in order. But that's only because the optimizer, I mean, there's no such thing as like an ordered aggregate. So if the optimizer was like, oh, I put in a sort operator just to tease that out, he would not be wrong in doing it.
The question is from Erland, I think, or the comment, is that there's no such thing as an ordered aggregate, but there is, because I've just created it.
Yeah, but, I mean, there's...
I'm playing a game. This is a game that we're playing with the optimizer, and it's a bet. Now, this is a bet I'm willing to make, is that, okay, so in theory, in some alternate universe, the SQL Server team could write some optimization code that would reach into my C#, figure out what I'm going to do with the value, and then optimize it away so it wouldn't have to do that work anymore. Is that going to happen?
No, what I was trying to say is the fact that because you put in the row number because you needed the aggregator to call an order, but if they would decide that, oh, for whatever reasons, we're going to put in a sort operator because when we need that later, before we call the aggregator, they were not breaking any guarantees if they would do so. But your aggregator is good enough.
No, there is a guarantee that's, okay, so I think, Erlen, what you're saying is that the sort, it isn't here at all because I have the data in the right index order, or these things, which are used to calculate the row number, could be moved in the plan?
Yeah, well, basically, if they would for some other reason think it would be fun to put in a sort between the sequence project and the
Oh, okay, so you're saying that a sort could appear between here and here, which would screw up the aggregate. That's true. If such a sort were included, that would screw up the aggregate. You're right.
because
However,
they're not making
why would SQL Server resort the data for the stream?
question, but they're not making guarantees that you
No, there's no guarantees of anything here. So this is a technique. This technique is not for everyone. I think, hopefully, I mean, that should be clear at this point. This technique is for those of you who are willing to take a bet in order to get the best possible performance. That's what people hire me to do, basically. The people who hire me want really, really, really good performance. So one of the guys who hired me said he wanted a Ferrari, and he doesn't care if sometimes it crashes and explodes. He wants the Ferrari, so 99% of the time, he has a Ferrari. Maybe even less than 1%. Maybe 0.5% of the time, he has a burning car. But the rest of the time, he has a really, really, really fast car. And he's willing to make that. He's a hedge fund manager, the person who told me, he gave me that rule. And he's perfectly happy with me using techniques like this. Now, if, on the other hand, you're working in, let's say, some healthcare field and someone's life stands in the balance based on the result of this aggregate, maybe this technique isn't for you, right? Different things for different use cases. So hopefully that's clear. Yes, Thomas?
The garbage collector, could you, if you slapped on a weak reference on it, wouldn't you prevent that problem from even occurring in the first place if it does occur?
So the question is, if I put a weak reference on the boundless array, would I prevent a problem? I would cause a problem in that case. So a weak reference is a reference that is held by your application or by your program. And when the garbage collector kicks in, the garbage collector, you're telling the garbage collector, I'm going to hold this reference, but you're allowed to clean it up if you want.
No. If there's a weak reference, you're not allowed to.
No, weak reference you are allowed to clean up. That's the point of.
As long as that reference stays in the
That's the point of weak reference, is that you're saying to the garbage collector, I'm willing to recreate this reference later. If you need the memory, feel free to clean it up, and it's, that's what weak reference is.
You will prevent.
We'll look it up after,
Touch that data.
we'll look it up after the talk, and you'll owe me some money. You're thinking of something else.
The weak reference class, if you put that on there and slap it on the on that array that you have, the boundary server, you should not collect it ever.
That would be a normal reference.
No, but the problem is that you don't have a normal reference you can hold.
I do have a normal reference.
Then why are you worried about the garbage collection in the first place?
Ah, hold on. First of all, I have a normal reference. This is just a reference. This will never be collected by the garbage collector. But there is a remote possibility that my app domain will be unloaded here. Actually, let's make it happen.
Right. Okay. So you're worried you will unload the app domain while it's running.
Yep. dbcc free system cache all. That will empty the app domain. Let's run it midstream. Let's see if I can get over there fast enough to make it happen. So I'm going to run this, and then I'm going to flip to the other window really fast and hit F5. There we go. And that's perfect. That's wonderful. I unloaded the app domain, got an exception. Therefore, my application knows that any data it got is invalid and it needs to rerun. I'm perfectly happy with that behavior. If you're not happy with handling exceptions in your application, again, maybe this technique isn't for you. If you're happy with that, this is a safety net as far as I'm concerned. This tells my application something bad happened, try again. Or, tells the user something bad happened, try again. So, and if I rerun now, my app domain gets reloaded, and nothing bad. It's a little bit slower the first time because of JIT, but I'm perfectly happy with that. So.
So the garbage collection, at some point that array you had must be garbage collected because else you have a memory.
At some point, the array I had has to be garbage collected, or I will have a memory leak. So what my code does is it reads the data out, and then somewhere in here, anyway, you'll have to trust me on this. I don't know exactly where it is, but somewhere in here, the code actually throws out the data. I think it's in the terminate method. So it goes through, starts processing the data, and as it's processing it, it basically takes the rows off and dereferences them so that the garbage collector can then come along and clean it all up. So there is no memory leak here. What we do keep around is instances of the interval ag class itself, but that is not going to leak. That's not really a leak because the managed thread IDs actually get reused by SQL Server. So chances are good that we're going to have a couple maybe in there that aren't reused very often, but that's nothing. That's no big deal. You don't believe me?
I don't. Oh, just ask.
All right. We have just a few minutes left. Oh, one in the back. So if the managed thread ID gets reused by SQL Server, what happens to the data that was aggregated on the previous run? There will be no data from the previous run because the data will have all been thrown out on the previous run. And the first thing that happens when we call into the aggregate, user-defined aggregate, is it calls this method init. And the first thing init does is produces a new counter. And so each time we call in here, on a new, for a new hotel, we're going to be on a different thread than all the other hotels that are currently processing. And the first thing we're going to do is call init, bring up a new counter, fresh start. So there's no risk of repeated data or anything like that. So, all right. So I actually wrote 2 other demos, but I did mark them as optional. And I won't run them, but I just want to tell you what they are. If you grab the download, I mentioned the parameter scalability issue and how the more data we pass into the interval, it kind of gets a little bit slower with respect to the store procedure. If you want to test that yourself and kind of see where those boundaries are, I wrote something called interval ag read only more params, where I passed a bunch of extra data in, and I wrote a store procedure that does the same thing called read hotel stays more data. You can run that. And then I also wrote a sample. One of the things that I do to, so if I run this store procedure again quickly, what you might notice, so if you look at the results here, I have a hotel name, and those of you with very sharp eyes might have noticed that when I ran the get hotel stay interval counts, I did not get a hotel name, I instead got a hotel ID back. And that is because later I wrote another example, which was optional, over here, but you should definitely look at it if you're interested. And I wrote a cache that caches the data dynamically into the CLR space. So as you need it, it lazy loads the cache. And you should definitely read and look through that sample a little bit. One of the things I do, which really scares the DBAs, is I cache data in SQLCLR so that I don't have to go read it. So all I need is my hotel ID in my stored procedure, because at the end of the day, I'm going to read the hotel name rather than pass it in every time. I'm going to read it from the cache and make things even faster. My cache is completely lazy loading and clearable so that I can control it, and if the app domain gets cleared, it'll reload itself automatically the first time it's invoked. So don't have to worry about that either. I think I've solved all the problems, basically, except, the query optimizer. So anyway, we are just about out of time. I'd like to thank you very, very much for joining me. I hope you learned something somewhat useful, and hope you saw that CLR will help you make your biggest, most analytical queries faster. SQL OS and the query optimizer might get in your way a little bit, but you can work around that. And hopefully you will look at new ways of solving all your old problems. Thanks again.